Um, Hello everyone, welcome to OneClass. My name is Shanjida, and today I'll be going over some commonly asked chemistry questions both at the high school slash university levels, college levels, and a bit about me. I am currently a second year human biology student, and if anyone needs additional schoolwork help or needs tutoring services, you guys could check out the description box below. Other than that, we'll get started. So the first question here says, which of the following are meso compounds? So we're given nine compounds here, and we're supposed to figure out which one of them are meso. And so meso compounds, just write this down, compounds meso compounds have a plane of symmetry. Plane plane of symmetry. And so what I mean by that are like some chemical compounds, um, even if they have a chiral center, they are not chiral molecules. So that's this occurs because their mirror image is superimposable and thus identical. Um, so basically your chiral centers, they don't really have so basically if you cut them in half, if you divide a compound into half, you will have you'll basically have the um same substituents on each of the sides, and they're on the same side of the plane. And so for example, um we could look at you could basically say which ones are meso compounds here. So for A, so A is a meso compound. So A, let's draw this. So basically A here, you can see that you have two carbons, um, bromine, hydrogen, and plane. You have a methyl group. So you have CH3 right here. And so for this case, it's the same thing. We are the top, H is going backwards, and your methyl group is coming towards you. H. And so this is a meso compound. Since if you want to break this apart, right, like that, you would have the same substituents on the same side. Therefore, they're identical. Um, so the next chiral or the next meso compound we have would be C in this case, and I'll show you. So basically, what we have for C, we have a chair conformation. So conformation. So we have a methyl group, H3. We have OH and a okay. And so to check if this is how I know that this is a meso compound is that you can cut this way, and you would basically have the same substituents on both sides, right? You would have an OH, a methyl, and a methyl on this side, and an OH on this side. So this is a meso compound. So the next one that we have here, in this case, it would also be D, since D looks somewhat similar to C, and so we can draw out D here. And so D is also a chair conformation. So we have a methyl CH3 OH OH, and if you want to cut this, you have so you will, if you would want to cut this, you would cut it diagonally, and so that you have it on the same side. And so basically this is also, so if you want to turn this, rotate this 180 degrees, you would get the same conformation basically. It would be the same. Okay, and so the next one that we have would be that we would have would be F. So I'll show you how F is a meso compound. Oops. F. Okay, so F, this is, we would do this like CH2 OH H, and this is H sticking out. H, and you have, so you can basically see how this can be a meso compound if you just set this line over here, right through the middle, right here. You would have the same stuff on the same side, and so this is a meso compound. And lastly, I think is would be I. Okay, and I'll show you how I is one as well. Okay, so I, we have fish projection or Newman projection. So we have and then we have, okay, so we have CH2OH OH going backwards, OH, CH2OH H. Okay, and so what you can do here is cut this also right to the middle, and you would have the same stuff on the same side. And if you rotated it 120 degrees, and so these are your meso compounds. These 1, 2, 3, 4, 5 of them, and so the rest from here would be so the rest would be all non-meso compounds, which are the ones, for example, B would be non-meso, E in this case, H and G would all be non-meso compounds since they don't have a plane of symmetry, and if you rotated 180 degrees, it won't be the same thing. And so your only meso compounds are um, A, D, F, and I, and so those are the answers. Yeah. Is correct. Okay, so our next question says, draw the Lewis structure of sulfur chloride, and how many, so it has ABC, how many shared pairs are in this molecule, how many lone pairs are in sulfur, what is the SCl bond order. Okay, so to approach this question, we first have to say, when you're drawing a Lewis structure, basically the total number of electrons that are shared among the two atoms in this case are distributed and that need to be distributed among each other. So if a formal charge is present on the molecule, that also needs to be taken into account of total number of electrons. So uh, if an atom has valence electrons, those need to be counted in as total number of electrons, even though they're not bonding. But so basically, a skeletal structure is first written by distributing bonds. Okay, and it also needs to fulfill octet rule, and the least number of formal charge, or the one that has the smaller charge, is the most stable on the atoms. So basically, we can say that so for example, SCl2, if you would count, Cl chlorine has 7 valence electrons, and in this case we have 2, so this would be 14 valence electrons. And so sulfur, since we only have 1 sulfur, has 6 valence electrons. And so if you add this all up, you have in total 20 valence electrons total. So and so the way they are arranged would be like this. So the way they would be arranged, so you have sulfur in the middle, and it is attached to 2 chlorine molecules. And if you want to write out, or it has 6 valence, actually, yeah, it does, and it has 6 valence electrons, and it would have 2 lone pairs where it's bonding the other 2 electrons with the chlorine. And so you can see sulfur will then have 2 lone pairs, whereas chlorine would have 3. In this case. And so for A, how many shared pairs are in the molecule? There are 2 shared pairs of bonding pairs, both of which are single bonds between sulfur and chlorine. So to write this out, you can say for A, 2 shared pairs paired pairs in a single bond. Okay, so now for B, so it says how many lone pairs are on the sulfur atom. So since sulfur, as I mentioned, is bonding with two electrons, it's sharing two electrons. It needs four more electrons to complete the octet. So basically, as you guys can see, sulfur has two lone pairs. Sulfur has two lone lone and for C, what is the sulfur chlorine bond order? So basically the bond order. So basically the bond order of sulfur and chlorine is 1 because there are a total of two sulfur chlorine bonds and two bonding pairs. So bond order is 1, and this is because total of two sulfur slash or sulfur and chlorine bonds and two bonding pairs. And two bonding pairs. And so this is the answer. And so this is what we have got. And yes. Right. Okay. Okay, so our third question says a solution of methylamine, which is a weak base, has an initial concentration of 0.401 molars. Methylamine has a equilibrium constant of 4.4 times 10 to the power negative 4. Calculate the pH. Calculate the percent of methylamine that is protonated. Okay, so we are given the molarity, we're given the Kb, and so this is an equilibrium acid-base equilibrium equation. And so to do this, let's first write out the equation. And so in this case, it would be CH. We're given the formula CH3 NH2. This is aqueous. And then you're always reacting with water, H2O. Given. And then this is an equilibrium equation, so you have that sign, CH, and it makes CH3 NH CH3 NH3 plus. This is also aqueous plus, and you basically give off OH. Since we know this because we're given our equilibrium constant of a base, so you know that it would produce a base. And so your Kb, as noted, is given as 4.4 times 10 to the power negative 4. right? And so now what we're gonna do, we have to now make an ice table, basically, um, where you have where you basically have your change in concentration and equilibrium. So what you have after equilibrium and what you had initially. So if you have an ice table, I would write this I E. So we take our solution, our base we have in the beginning, and it says we have 0.401 molars. So we have 0.41 and 0.1 molars, and our change in this case is negative x, since we are getting, so since we're going from products, so reactants to products, it would be negative, so your reactants are always negative. Um, and then we have what we have next. We basically have our equilibrium in this case would be 0.401 minus x. Um, this is for your reactants, and then for your products, um, it doesn't have an initial concentration yet, so both of them will be 0. So we don't need so we're not considering water in this case, since it's a liquid, it's not really a solution. So then our change for our products would be positive, and then our equilibrium in this case would be x and x, since there's no coefficient either. Okay, and then if we were to now write this out in our KB expression, the way we would write this is by basically writing it KB is equal to the concentration of your products, which is CH 3 NH3 plus OH negative, and all over your reactant, which in this case is methylamine, CH2 also H3 NH2. And so now what we're going to do is just plug in the values we got from the table into this equation. So since our variables for our products, or the numerator, is both x, so we can write this as x squared all over what we have for our reactant, which is 0.401 minus x, and we could just write this here, which is 0.401 x. And now what we're going to do, and so we know that this is equal, to our KB constant, which is 4.4 times 10 to the power negative 4, right? And so we can calculate x using the quadratic formula, but we can use an often valid assumption that is, we can also say that since this is a really small number, that 0.401 minus x is actually equal to 0.401. You can also say that that's an assumption. And so we can basically say that since we can also, so since basically your x over here gets neglected, since you can basically, since this is a really small number, you can basically neglect x in this case. And now what you can say is that x squared over 0.41, so you just got rid of your negative x right here, is equal to your KB constant, which is 4.4 times 10 to the power negative 4. And then just solve for x. And for x, just you just square root this, and you have 0.401 times your KB constant, 4 times 4 times 10 to the power negative 4, all square root, and then what you get here is 0.013. Okay, and we could say that this is the concentration of, which is equal to OH. So we can basically say the concentration of OH is 0.013 molars. Okay, and since we found the concentration of our base, we can now calculate, we can basically now calculate the pH or the POH in this case from the concentration of our base. And to do that, we can now say that, so if you guys recall that POH is equal to the negative log of the concentration of OH over base. And so the log of 0.013 molars, you get here basically get 1.89. Since this is POH, we want to find pH. So what we need to do is find pH. Since pH, well, since there's an equation, pH plus POH is equal to 14. So, for example, now pH is equal to, oops, this is supposed to be 14, is equal to, this is equal to 14 minus POH. So your pH would be 14 subtracted by your POH, which is 1.89. And what you get here is 12.11 as your pH. So as you can see, this is pretty basic, and that's why it is a base. And so this is your pH. And so the last question says to calculate the percent of methylamine that is protonated. And to do that, so we can say the percent, the percent of protonated. We can basically do this by having having a ratio of our final and our initial concentration, which is 0.013 molars over our initial, which was 0.401. And you just times this percent, and what you get here, you get 3.24%. So this is how much it was protonated, or became, or this is how much acid it produced or became. Okay. And so this should is correct. Okay, so our next question here says, draw the Lewis structure for the ammonia NH3 molecule. Be sure to include all the resonance structures that satisfy the octet rule. Okay, so what we need to do is first find the total number of valence electrons of each of the atoms. So NH3 in this case. So now let's break this into N and 3 H's. So nitrogen has 5 valence, 5 valence electrons, and hydrogen has 1. So in this case, it would have 3 since we have 3 valence electrons. Okay, and so now the total number, the total number of valence electrons we have is 8 total, 8 valence electrons, right? And so secondly, what we need to do is just come up with a skeletal structure by joining the atoms through covalent, single covalent bonds. Okay? So we can arbitrarily just draw this like this, having our nitrogen as a central atom. This is also because you can see that there's 3 hydrogens, and so the one that has the most atoms would likely to be branched off of the central atom, and also because nitrogen is more electronegative than hydrogen, so this is why it's the central atom. And so then third, what we can do is subtract 2 electrons for each bond in the skeletal structure. So the 3 bonds in this, right? We have 3 bonds. 1, 2, 3. The 3 bonds in the structures account for 6 of the 8 valence electrons. And so since there are 6 valence electrons being shared among the two, that means we have 6 valence electrons being shared. And so there are two more electrons left, right? And so that needs to be assigned. And so what the next step would be, since we know that we can basically say that since nitrogen has 5 electrons, 5 valence electrons, it's sharing only 3. So you guys could probably say that, the 2 more electrons would be on nitrogen. And so lastly, our structure would look like this. Okay, with having the 2 electrons on the nitrogen atom, and this is your complete octet. So complete octet. And so this is how you draw the loose structure of ammonia. And yeah, so it doesn't have any resonance structures, since for resonance structures you need pi bonds and carbon. Oh, you need pi bonds and so this and sigma pi bonds, and in this case you don't, so you can't really, and it already reached its complete octet. So, ammonia does not have it. Okay, so our next question here says, here to consider the reaction of sulfuric acid with sodium hydroxide. Okay, suppose a beaker contains 38.4 milliliters of 0.188 molars of sulfuric acid How many milliliters of 0.332 molars of NaOH must be added to react completely with sulfuric acid? Okay, so what we need to find here is volume of sodium hydroxide. So we're given, right, the equation. We're given that H2O. We're given H2O, H2SO4, sorry, aqueous plus 2Na or H aqueous reacts with 2H2O liquid and plus Na2SO4. Yes. Okay, so this is balanced. And so we're trying to find out volume. Volume of NaOH, right? So we are given the volume for sulfuric acid and the concentration of sulfuric acid and the concentration of sodium hydroxide. And so we can say, so now what we can say, I'll just write out what we know. So given we have volume of H2SO4, which is volume of the 38.4 milliliters. We're also given the concentration. We should always convert it into liters, since molarity is in liters, moles per liter. So this would basically become 0.0384 liters. And then the molarity, then I'm saying molarity of H2SO4 is given as 0.188 molars, or you can say 0.188 moles per liter. So we're given this, and we're given the molarity of NaOH, which is 0.33. Okay, and so what we need to do, so therefore we can say the number of moles. So the next step would be to find the number of moles of H2SO4, since we have the volume and the molarity. So like now we can say number of moles of H2SO4. We have so number of moles would be, so since molarity is equal to N over V, moles is equal to M times V. And so molarity, we're given that it's 0.188. Multiply this with the volume, which is 0.0384 liters moles per liter. And so what you have is 0.00722 moles of H2SO4. Okay, and so you can see from the equation that we have here, you can see that this is a 1:2 ratio of sulfuric acid to sodium hydroxide. And so you can probably imagine that the number of moles would be doubled for sodium hydroxide. And so what you have, so the ratio, the mole ratio, so the mole ratio, the mole ratio of H2SO4 to NaOH to NaOH is um, is basically 1 to 2, 1 to 2, and so basically, therefore, the number of moles would be 0.00722 times 2, which is 0.0144 moles of NaOH that has reacted. Okay. And so now we can find, so since we're given the molarity of NaOH, we can use this to find the volume now. So since molarity or concentration is equal to N over V, we can now find the volume, which would be, so in this case, if we were to, so in this case, volume would equal to N over C. So the volume of NaOH, so the moles given, we have the moles that we're given, and so V of NaOH. So the moles that we have is 0.0144 moles, and the concentration that is given, we have 0.332 moles per liter. So the moles get cancelled out, and what you're left with is what you have is 43.4 oops 43 so what you have in liters, sorry, it's going to be 0.0434 liters, and you can convert this into milliliters by multiplying this by 1,000. You have 43.4 milliliters. Okay, so this is your volume of NaOH. That needs to be added to react completely with sulfur. Okay. Yes. Right. Okay, so our next question here says the connectivity of HNO would be either HNO or HON. Draw a Lewis structure for each and predict which connectivity is more favorable arrangement. Okay, so let's calculate the number of valence electrons. So we know, so H and O. Right, so this has, so one H, one hydrogen, has one valence electron. And then we have one nitrogen. This has 5 valence electrons. And then we have one oxygen, and this has 6 valence electrons. And if you add this up, we have 12 in total, 12 valence electrons. Okay. Okay, so now let's just draw the Lewis structure using the following arrangement. We can basically, so since it's HNO, we can probably guess that this would be the arrangement HNO. So the two bonds represent 4 of the 12 valence electrons, where 4 of them are being shared out of the 12. So there are 8 valence electrons left, right? So 8 left in this case. Okay, and so what we can do, we can then complete the octet of the terminal the terminal oxygen right here, and add the remaining valence electrons to the nitrogen. Since hydrogen already completed its octet, basically it's already full, so we can give the remaining to the oxygen first and then to nitrogen. Okay, so let's see. So oxygen would have 3 lone pairs in this case, and then nitrogen in this case would have 2. Okay, and so what we can see from here, we can see that that your nitrogen atom doesn't have an octet yet, right? So we form a double bond between, since it only has 3 bonds, it could make 5 bonds. Basically, or it no, sorry, it could make 4 bonds basically, and what we can, or no, it can make 3 bonds, and it has 2 lone pairs. Since it's only bonding with 2, we need 1 more, and so to do that, we can basically put a double bond with the oxygen. And so what we can say here, since we still have the lone pairs double bonded with an oxygen, and so that means oxygen will lose pair of its lone pairs, and so this is how it will become. And so this is the structure for HNO. However, if we want to draw HON, in this case the question is asking, we can draw it the same way. Like, keep in mind we still have the same number of valence electrons, and we have HON, and so we could just assign the valence electrons to the terminal atom here would be this, and our central atom would. So we can say that the oxygen doesn't have an octet yet, so we form a double bond between the O and the N atoms. Okay, and so what we can do here is create a double bond between oxygen and nitrogen. So then oxygen basically basically gains a formal charge of plus, and nitrogen loses a lone pair and it gets negative. And so in this case, the oxygen and nitrogen atom carry a formal charge, as you guys can see. And so when you're comparing the two Lewis structures that we have, the structure with the connectivity of HNO is more favorable since it doesn't contain any formal charges. So in this case, the one that would be more favorable would be HNO, since it doesn't have any formal charges, whereas HON carries a formal charge. Okay, so this case HNO would be the more favorable. and then HON, because it doesn't have formal charges. Okay. So yeah, you guys can see how oxygen has formal charge +1. Nitrogen has negative, so the solution is correct. Okay. The next question says, what is the conjugate acid of ammonia and the conjugate base of sulfuric acid? Okay, so conjugate. Okay, so the conjugate acid, okay, acid, acid of ammonia, NH3. So since ammonia is a really weak base, so the conjugate acid is pretty neutral. I mean, ammonia. So when you're talking about an acid, an acid, an acid, will donate a proton. This case, so proton as in a hydrogen ion, and form a conjugate base. A conjugate base. Okay. Whereas a base, a base can receive or gain a proton. We're talking about Lewis acid bases, and receive a proton and form a conjugate acid, right? Since when we're talking about acids and bases, your acids have more hydrogens, your bases, or any bases would have more hydroxide ions, OH ions, and so therefore the conjugate acid, when we're trying to go to an acid, your acid would have more hydrogens. So conjugate acid of NH3, you just have to add a proton, would be NH4 plus, since you added it. And then, so basically now a conjugate base, so conjugate base of H2SO4. So this would be, so you would mind, so basically a conjugate base will, to make it a conjugate base, you need to lose protons. That means that this is an acid, so it would give off a proton, and so this would become HSO4 minus. Okay, since this is an acid and it would give off its hydrogen, a proton, to form another acid, basically. Okay, and so this is the answer, and this So, uh, solution. What's our next question? Here it says, what are the resonance structures for sulfurous acid H2SO3? Okay, so let's draw out the structure. We have S double bonded to an O. Also, you would also have to include all the lone pairs of each atom in this case. So, oops, OH, H. In this case, this oxygen has two. Um, and this one, and sulfur would have two. And to make it a resonance structure, what we can do is basically move this pi bond up here, and this will then become three lone pairs, become a negative. And you have two lone pairs. Okay. This is the resonance structure for sulfurous acid. There's two, and if you want to do another one, it would basically go to the same thing that it was before. So these two are the resonance structure for sulfurous acid. And right. And so basically, that was the end of our session. If you guys like this Q&A, please subscribe to this channel, comment, share this video. And other than that, I'm Shanjida. I'll hope to see you guys soon. And if anyone has any personal questions or want to have a one-on-one tutor, please check the description box below and follow the links to ask your questions. And I'll hope to see you guys soon. Bye-bye.